Most main battle tanks are becoming expensive paperweights in the freezing mud of the high north. While heavy armor sinks into the tundra, Sweden's CV90 and the Lynx KF41 are rewriting the rules of polar engagement. Discover how rubber tracks and thermal masking are turning these platforms into NATO's ultimate Arctic predators. NATO is quietly shifting its entire defensive strategy toward a frontier where traditional steel fails. It isn't just about firepower anymore. It's about surviving in -40 degrees, where the environment is as deadly as the enemy. We're diving into why the CV90 and Lynx KF41 have become the new gold standard for high-latitude warfare. Imagine a 40-ton beast that can disappear from thermal sensors while gliding over deep snow that stops a Leopard 2 dead in its tracks. This is the reality of modern modular design. Today, we analyze the radical engineering behind the CV90 and Lynx KF41 that allows NATO to maintain tactical dominance across the world's most brutal terrains. 60-ton main battle tank advancing across a frozen northern landscape. Its armor is powerful, its cannon is devastating, and its engine produces enormous torque. But suddenly, the ground beneath it begins to move. The snow hides waterlogged soil, the ice is thinner than expected, and permafrost that once supported heavy vehicles has softened into mud. Within seconds, one of the most powerful combat machines in the world is no longer advancing. It is sinking. Now imagine a smaller tracked vehicle quietly moving around it, carrying infantry, drones, sensors, and anti-armor weapons while remaining more difficult to detect. This is not simply a story about lighter vehicles defeating heavier ones. It is about how the Arctic battlefield is changing the meaning of military power. Welcome to Skyjet Wings. Today, we are examining why Sweden's CV90 and Rheinmetall's Lynx KF41 are emerging as possible blueprints for future warfare in the high north. Some of the claims surrounding these vehicles are real, while others are exaggerated. The truth, however, is even more interesting. For more than a century, armored warfare followed a simple principle. Greater protection usually meant greater weight. But the Arctic challenges that logic. A heavy tank may dominate firm terrain, yet deep snow, wetlands, thawing ground, and muskeg can turn weight into a serious operational disadvantage. The key factor is not weight alone, it is ground pressure. Ground pressure measures how much of a vehicle's weight is concentrated on the surface beneath its tracks. Wider or longer track contact areas spread that weight across more terrain. This can reduce sinking and improve movement over soft surfaces. That is where the CV90 becomes particularly interesting. The CV90 family was designed around mobility, adaptability, and operation across difficult terrain. Its comparatively balanced weight and broad track contact help it move across snow, forest, and soft ground more effectively than many heavier armored vehicles. However, the CV90 does not possess a magical track system that makes it impossible to become stuck. Different variants and operators use different track configurations, while snow depth, vehicle weight, driver skill, and soil conditions still matter. Even so, its basic design philosophy is highly relevant. Instead of placing maximum armor on the smallest possible footprint, the CV90 balances protection, firepower, and terrain mobility. This gives commanders something extremely valuable in the Arctic: route freedom. A heavy tank may be restricted to reinforced roads, bridges, and carefully surveyed corridors. A vehicle with lower ground pressure may have more options to move through forests, snowfields, and softer terrain. That matters because predictable movement is dangerous. Once an enemy knows which roads a heavy armored unit must use, those roads can be monitored by drones, mined, targeted by artillery, or blocked by destroyed infrastructure. My personal assessment is that main battle tanks are not becoming obsolete in the Arctic. Their firepower and protection remain extremely important, but they may increasingly require lighter tracked vehicles to scout routes, secure flanks, carry infantry, and operate where the heaviest armor cannot safely travel. The future Arctic force will not choose between tanks and infantry fighting vehicles. It will combine them, but the lighter platforms may determine where the entire force is able to go. Now we reach one of the most overlooked aspects of armored warfare: sound. Traditional steel tracks create repeated metal-on-metal impacts. At speed, an approaching tracked vehicle can generate significant vibration and mechanical noise. That noise does more than reveal the vehicle. It affects the people and equipment inside it. Rheinmetall has successfully tested composite rubber tracks on the Lynx KF41, showing that the vehicle can operate with them and later be returned to steel tracks if required. This means rubber tracks are a tested option for the Lynx, although they are not necessarily standard on every vehicle. Composite rubber tracks can reduce vibration and acoustic signature because they avoid some of the steel-on-steel interaction found in conventional track systems. Lower vibration can also reduce crew fatigue and mechanical stress on onboard components. Imagine spending 12 hours inside an armored vehicle crossing frozen, uneven terrain. Every impact travels through the suspension. Every vibration reaches radios, displays, optical systems, connectors, and ammunition storage. Reducing those forces could allow crews to remain alert for longer while potentially lowering wear on sensitive electronics. In an Arctic environment where repair teams may be hundreds of kilometers away, reliability becomes a combat capability. But rubber tracks do not make the Lynx silent. The diesel engine, cooling system, suspension, snow displacement, and transmission still produce detectable noise. What rubber tracks can do is reduce one part of the vehicle's overall signature. That difference could become critical during night movement, dispersal, or an attempt to approach an enemy position without giving additional warning. In a frozen environment, heat becomes evidence. A warm engine compartment against a snow-covered background can appear extremely clearly through thermal optics. Exhaust gases may form a visible heat plume, while tracks, road wheels, and mechanical components can retain heat after movement. Today, a small drone carrying an infrared camera may be able to search an enormous area without exposing a human reconnaissance team. This is why multispectral camouflage systems, such as Saab's Barracuda mobile camouflage system, are receiving growing attention. Barracuda is designed to reduce detection across several parts of the electromagnetic spectrum, including visual, near-infrared, thermal infrared, and radar bands. It can also be configured for Arctic surroundings. The system does not simply paint a vehicle white. Its purpose is to alter how the vehicle appears to different sensors while reducing the contrast between hot vehicle surfaces and the surrounding environment. But camouflage is not an invisibility cloak. A moving vehicle still disturbs snow, leaves tracks, produces exhaust, reflects radar energy, transmits radio signals, and may become visible from angles the camouflage package was not designed to defeat. There is also no credible public evidence that rubber tracks alone make the Lynx nearly invisible to Russian-made infrared sensors. Rubber and steel can retain and transfer heat differently, but the engine, exhaust, and cooling airflow remain much larger thermal signature problems. The more realistic advantage comes from combining several measures, including thermal insulation, exhaust management, reduced idling, multispectral camouflage, shorter exposure times, and disciplined movement. In my opinion, the winner of future Arctic combat may not be the vehicle with the thickest armor. It may be the vehicle that is detected 30 seconds later. On a battlefield filled with drones and loitering munitions, 30 seconds could decide whether a vehicle completes its mission or becomes a target. Mobility and camouflage are only part of the story. The CV90 and Lynx KF41 are also being built around digital adaptability. Modern CV90 configurations use scalable electronic architecture that can integrate battlefield management systems, sensors, defensive technologies, and communication networks. This allows vehicles to exchange information with other ground forces, aircraft, drones, artillery units, and command centers. That does not prove that every CV90 can currently command a swarm of autonomous drones, but it creates the architecture needed to connect vehicles with unmanned aircraft and reconnaissance systems. A CV90 could receive a drone image of an enemy position, share the coordinates with another unit, and reposition before the opposing force even understands it has been detected. The Lynx follows a similar philosophy. Rheinmetall describes the KF41 as having a digital backbone and open architecture intended to make the integration of new mission systems easier. Its protection systems and mission modules are also designed to be expandable and adaptable. This does not mean an anti-drone electronic warfare package can be installed instantly without testing. Power requirements, antennas, electromagnetic interference, software compatibility, and Arctic environmental protection would all need to be addressed. However, open architecture can shorten the pathway from identifying a threat to integrating a response. That is crucial because drone technology is evolving far faster than traditional armored procurement cycles. A vehicle designed around fixed electronics may become outdated before its production run is complete. A digitally adaptable platform can receive new sensors, software, and counter-drone equipment throughout its service life. The next major step could be AI-supported terrain analysis. Data from satellites, drones, temperature sensors, and reconnaissance units could help crews identify weak ice, deep snow, steep slopes, soft ground, and likely ambush zones. Public evidence does not confirm that CV90s and Lynx vehicles are already autonomously plotting safe routes across thinning Arctic ice, but technically, their digital architectures make this kind of decision support capability increasingly possible. I believe this is where the real revolution will occur. It will not replace the driver, it will give the driver information that no human crew could collect alone.
Why is all this happening now? Because the Arctic has moved from the edge of strategic planning towards its center. NATO has increased its focus on the high north through expanded exercises, multinational deployments, and stronger regional coordination. Changing sea access, military activity, thinning ice, and growing competition over northern routes have made the Arctic more strategically important. The region contains shipping lanes, energy infrastructure, undersea communications, and vast natural resources. Static defense is extremely difficult across such an enormous region. A fixed position can be bypassed, a large base can be monitored, and a supply hub can be targeted. That is why mobile, dispersed, and digitally connected forces are becoming more attractive. The CV90 and Lynx KF41 fit this concept because they are not single-purpose vehicles. Their chassis can support infantry, command, reconnaissance, recovery, air defense, and other mission configurations. Instead of deploying a collection of completely unrelated vehicles, an army can build several capabilities around a common platform family. This simplifies training, maintenance, and logistics, which become even more important when every spare part must travel through extreme weather and long supply routes. So, are the CV90 and Lynx KF41 the new kings of Arctic warfare? Not yet. Neither vehicle is invulnerable. Neither can ignore terrain. Neither becomes invisible simply by using rubber tracks or multispectral camouflage. But together, they represent a major shift in armored warfare. They show the movement from maximum weight to balanced ground pressure, from steel-only mobility to quieter track alternatives, from camouflage paint to multispectral signature management, from isolated vehicles to digitally connected combat nodes, and from rigid designs to platforms that can evolve as the threat changes. My conclusion is simple. The future of Arctic warfare will not belong only to the vehicle carrying the largest gun. It will belong to the force that can move where the enemy cannot, remain hidden for longer, share information faster, and adapt before the battlefield changes again. The CV90 and Lynx KF41 may not replace the main battle tank, but they could determine whether that tank ever reaches the fight. What do you think? Will lighter, digitally connected infantry fighting vehicles dominate the high north, or will heavy main battle tanks remain the decisive force? Share your opinion in the comments. For more original defense analysis, emerging military technology, and the latest strategic developments, like this video, subscribe, and turn on notifications for Skyjet Wings.